everyone, welcome to today's lesson. In the previous lesson, we introduced the classification of mechanical transmission systems. In this lesson, we will continue with Chapter 6 and explain the design of mechanical transmission systems. Let us look at the basic components of a belt drive. A belt drive consists of three parts: the driving pulley, the driven pulley, and the belt. The driving pulley is responsible for transmitting power. The driven pulley receives the power and drives the working machine. The belt is the core component that connects the two. In the picture, each component is labeled. 1 is the driving pulley, 2 is the driven pulley, and 3 is the belt. The diameter of the pulleys and the type of belt both affect the performance and efficiency of the transmission. According to the transmission principle, belt drives can be divided into friction belt drives and toothed belt drives. Friction belt drives rely on the friction force between the contact surfaces of the belt and pulleys to transmit power, commonly using flat belts, V-belts, and poly V-belts. Toothed belt drives transmit power through the meshing of the belt teeth with the pulley teeth, such as synchronous belts. On the left is an example of a friction belt drive, and on the right is the structure diagram of a synchronous belt drive, showing the meshing of the belt teeth with the pulley teeth. Belt drives have the following advantages. 1. They have good elasticity, can cushion and absorb vibration, run smoothly, and produce low noise. 2. They are suitable for transmissions between two shafts with a large center distance. 3. In the event of overload, slippage occurs, which prevents damage to other components and serves as protection. 4. They have a simple structure, are easy to manufacture and maintain, and have low cost. However, belt drives also have disadvantages. 1. They have a relatively large overall size and are not compact. 2. Elastic slip exists, the instantaneous transmission ratio is inaccurate, and the transmission precision is low. 3. The efficiency is relatively low, with V-belt transmission efficiency ranging from 0.87 to 0.96, and the belt has a relatively short service life. 4. During operation, a tensioning device is required, and the shafts and bearings that support the pulleys are subject to large forces. 5. They are not suitable for high temperature, flammable, or corrosive environments. Next, we will learn about the design of synchronous belts. A synchronous belt consists of the following parts, as shown in the figure. 1. The belt back connects the belt teeth and the tension member. 2. The tension member is the tensile element that ensures pitch stability. 3. The fabric layer increases wear resistance and strength. 4. The belt teeth engage with the synchronous pulley to transmit power. Synchronous belts come in two forms: single-sided teeth and double-sided teeth. Double-sided teeth can be divided into symmetrical and alternating arrangements. The figure shows the components of a synchronous belt and the two arrangements of double-sided teeth. A synchronous pulley usually consists of a toothed rim, flanges, and a hump. The toothed rim is used for engagement with the belt teeth, and the flanges prevent the synchronous belt from coming off. The main parameters of a pulley include: 1. The number of teeth. 2. The pitch diameter. 3. The width of the pulley. At present, the standard for trapezoidal tooth synchronous belts in China adopts inch-based pitch, while the arc tooth synchronous belts adopt metric pitch. The national standard is GB 11616, as shown in the figure. Next, let us study the structure and parameters of synchronous pulleys. 1. Structure and materials of synchronous pulleys. The structure of the pulley is as shown in the figure. To prevent the working belt from coming off, flanges are generally installed on both sides of small pulleys. The materials of pulleys are generally cast iron or steel. For high-speed, small power applications, plastic or aluminum alloy can be used. 2. Parameters and dimensions of synchronous pulleys. 1. The number of teeth of the pulley. 2. The pitch diameter of the pulley. 3. The pitch of the pulley. 4. The outside diameter of the pulley. 5. The width of the pulley. 3. Failure modes and design criteria of synchronous belt drives. The main failure modes of synchronous belt drives include fatigue damage of the tension member, shear failure of belt teeth, and crushing or wear of the belt tooth surface. Design calculations include determining the belt type, pitch length, belt width, center distance of the transmission, as well as the number and diameters of the driving and driven pulleys and other structural parameters. The specific design steps are shown in the figure, consisting of 11 points. Gear transmission has the advantages of a constant instantaneous transmission ratio, high transmission accuracy, the ability to withstand heavy loads, compact structure, low friction, and high efficiency. It is widely used in mechatronic products. 1. The types of gear transmission are classified into the following 4 categories. 1. Spur gear transmission. 2. Helical gear transmission. 3. Straight bevel gear transmission. 4. Herringbone gear transmission. 2. Classification by working conditions. Open gear transmission. Suitable for low speed and less critical situations, such as agricultural machinery, construction machinery, and simple equipment, with only simple protective covers. Closed gear transmission, with good lubrication and sealing, used in automobiles, machine tools, and aero engines. 3. Classification by tooth profile. Involute, commonly used, cycloidal, used in timing instruments. Circular arc, strong load carrying capacity. 4. Classification by application. Power gears, mainly for power transmission, usually high-speed heavy load or low-speed heavy load transmissions. Motion gears, mainly for accurate motion transmission, usually light load and high-precision transmissions. 5. Classification by tooth surface. Soft tooth surface gears, hard tooth surface gears. Common gear reduction devices are as shown in the figure. Next, let us study the calculation of the total transmission ratio of a gear transmission system. In the system shown in the figure, the motor drives the load through a gear reduction device. The motor has an inertia Jm and output torque Tm. The gear reducer has a transmission ratio I. The load has an inertia Jl and friction torque TLF, and the total transmission ratio is the ratio of the motor's angular displacement to the load's angular displacement, usually greater than 1. The torque of the system acceleration is shown in the figure. The optimal total transmission ratio of the gear transmission system is achieved when the equivalent inertia of the load reflected to the motor shaft equals the rotor inertia of the motor, which achieves the best match between the inertial load and the torque source. The optimal number of stages in a gear transmission chain and the best value for each stage's transmission ratio is achieved when the load moment of inertia JL converted to the motor shaft equals the rotor inertia of the motor JN. This ensures the best match between the inertial load and the torque source. The determination of the number of stages of the gear transmission chain and the distribution of the transmission ratio of each stage can be carried out according to the following 3 principles. The principle of minimum weight, as shown in the figure. The principle of minimum weight only applies to low-power systems and is not applicable to high-power systems. The principle of minimum angular error of the output shaft. Specifically, we need to consider how the angular errors of each gear stage are transmitted to the output shaft and calculate the final total angular error. The formula is as shown in the figure. Next, let us look at an example diagram, which shows a 4-stage gear transmission system. The input shaft drives gears 1 and 2, then transmits step by step to gears 3 and 4, and finally to the output shaft. From the formula, it can be seen that the accumulation of errors follows an inverse relationship with the transmission ratio. The larger the transmission ratio, the smaller the contribution of the error to the output shaft. The principle of minimum equivalent inertia. For servo transmission systems, it is often required to start, stop, and reverse quickly. This can shorten the transient process, improve response, and reduce starting power. The number of stages of the gear transmission chain and the distribution of the transmission ratio of each stage can be determined according to the principle of minimum equivalent inertia. The principle of minimum equivalent inertia. As shown in the right figure of the 2-stage gear train, the total transmission ratio is the product of the individual stage ratios. Assuming each driving pinion has the same rotational inertia, the inertias of shafts and bearings are negligible, and every gear can be approximated as a solid cylinder with identical tooth width and material, then the stage transmission ratios are as indicated in the figure. The same applies to an N-stage gear transmission system. Selection of the 3 principles. The design of a gear transmission device should take into account specific working conditions comprehensively. Harmonic gear transmission. The working principle of harmonic gear transmission. Harmonic gear transmission mainly consists of a wave generator, H, a flux spline 1, and a circular spline, 2, as shown in figure 6.11. The wave generator has 2 lobes and is called a double wave generator harmonic gear. The transmission ratio of harmonic gear transmission equals the angular velocity of the flux spline minus the angular velocity of the wave generator divided by the angular velocity of the circular spline minus the angular velocity of the wave generator, which is also equal to the ratio of the number of teeth of the circular spline to that of the flux spline. When the flux spline is fixed, its angular velocity is 0. A positive result indicates that the circular spline and the wave generator rotate in the same direction. When the circular spline is fixed, its angular velocity is 0. A negative result indicates that the circular spline and the wave generator rotate in opposite directions. Today, we have learned the design methods of belt drives, gear drives, and ball screw drives, and understood the advantages, disadvantages, and application scenarios of each transmission method. We have also learned important design calculation formulas. I hope everyone practices and reflects more after class. Thank you for listening. Goodbye.